morning, precalc fans. How are we doing on this fine Tuesday morning? A little chilly outside. Weatherman says it's going to get chillier this week on Thursday, Friday, and Saturday. Brr. But I looked in the long-range forecast. They're calling for nice weather next week. Towards the end of next week, they're calling for some nice weather. So let's keep our fingers crossed that holds true. And let's hope that they aren't correct about this weekend. Because after last weekend, when it was really, really nice out, well, we have to turn around and have some cold again. Anyways, we're going to do day 2 of dealing with basic vectors. Victor and IJ component notation. Tomorrow will be a review day over this material. Thursday will be the evaluation over this material. What we covered today, yesterday and today will be the evaluations. When we're talking about IJ notation is a way to be able to signify vectors a little bit easier than just doing what we did in trig class, where we just drew the line up there at a specific angle, and we dealt with vectors at that point and dealt with law signs and cosines. When dealing with IJ notation is a lot easier to work with when you're adding multiple vectors together. So it is a benefit to dealing with vectors. We want to draw the vector and also the resultant vector of this. Okay, and we're going to deal with the magnitude. Once again, to signify this is the magnitude, which is the length of the resultant vector. Okay, if we take a look at the vector 3i minus 4j, I is, once again, the horizontal component. Okay, what you can travel horizontally, j is what you can go vertically. Once again, I and j, I is horizontal, j is vertical, and these are unit vectors, which means they're a length of 1. But if you remember what we do with these coefficients are called the scalar multipliers. They are the scalar multipliers, so it only affects the length of the vector, not any direction of the vector. So this is 3 in the I direction. We have 3 i's going out. So we're going to go out 3 in the I direction. So we're going to go horizontally 3 units out to this point. And at this point, we're going to stop the first and we're going to start the second. Remember, addition of vectors, wherever we stop the first, we begin the second. As we dealt with vectors in trig class, we gave directions to your house. Wherever you stopped one direction, you started a second direction. Well, this tells me to go -4 in the j direction. So it's going to tell me to go down 4 in the j direction. So wherever I stop my first, I'm going to start my second, and I'm going to go down 4. So this is 3i, and this is minus 4j. And we've just added them together, because when we add together, remember, we go tail to tip. What we want to do is we want to draw the vectors and then the resultant vector, which is the solution to the addition of vectors. So I'm going to draw in my result vector, so I'm going to start here and end here. The shortcut to Grandma's house. Here is your resultant vector, and I want to find the magnitude of that resultant vector, Well, if you look at what we just developed there, we have a horizontal line, then we have a vertical line. What type of triangle did we form there? That is correct. We have a right triangle. And if we have a right triangle, we have our good old buddy Pythagoras. Whoopsie. Let's try that again. We have our good old buddy Pythagoras. There he is. There he is. We've been looking for him. Our good old buddy Pythagoras that will allow us to be able to find the magnitude of the resultant vector. So we have VR squared equals 3 squared plus a negative 4 squared. Or if you think back, what we have here is a 3, 4, 5 triangle. Make sure you watch your negatives here. We have 9 plus 16 is VR squared. So we have a value of 25, or we have a 3, 4, 5 triangle. A 3, 4, 5 triangle. So we can use our good old buddy Pythagoras to be able to determine a magnitude of the resultant vector. And really what we're doing here is just squaring each one of the components. We are squaring each one of the components. So we have our delta x squared plus our delta y squared, or we have VR squared is your delta h squared plus your delta v squared. These are just your components for your two vectors. We want to be able to determine a unit vector in the same direction as vector A. Well, how do we determine the unit vector in the same direction as unit A? Well, what we can do with this, a unit vector of any, to determine a unit vector in the same direction that we have our original vector. We want to now just reduce this down to one unit. How we can do that is to divide by our magnitudes, each one of our components. So vector A, its unit vector would be 3 over 5I minus 4 over 5J. Now, a unit vector has a length of 1. Now, if we prove this, what we have here is we have 3/5 squared plus a negative 4/5 squared. So we have 9 over 25 plus 16 over 25. We have 25 over 25, which is a value of 1. So our resultant vector squared is equal to this squared plus this squared, using our good old buddy Pythagoras. So we have VR squared is equal to 1, or VR is equal to 1. So by dividing by the magnitude of the vector, we can create a unit vector in the exact same direction. Addition and subtraction of vectors by looking at the components. Now, if we take a look at what we have here, I want to add A plus B. I want to add A plus B to find the result of A plus B. Well, what we did back in trig is we drew just two vectors together, draw in the third side of the triangle, and use our law of sines and cosines to be able to determine the magnitude of the resultant vector. What components allow us to do if we can break things down into components? Let's think about vector A is 4I plus 5J. So we have 4I and 5J. Now this is not going to be drawn to scale. So we have 4I and 5J. And the result to that would be this. But what we want to add to this is we want to add to this negative 6I plus 3J. So when we add to this, we are stopping at this point right here, and now we're going to go negative 6 in the I direction. So we're going to go negative 6 in the I direction. That would take me, let's see, that's 4. Then I go negative 6 in the I. So this would be negative 6I. And then I'm going to go 3 more in the J direction. So I'm going to go up 3 more. So my resultant vector then is where I originally started to where I ended. This would be my resultant vector. Well, let's take a look what happened with what we've done. We've gone out 4 in the I and we've come back 2 in the J. We've gone up 5 and then we've gone up 3. So if I take a look at my resultant vector, Victor, what have we done? We've gone, if I started here and ended up here, how many units did I go horizontally? I started at this spot and I ended up here. What did I do horizontally? Well, I went out 4 to the right, but then I went back 6 to the left, so I went back negative 2 in the I direction. My net is I go out 4 and I go back 6, so really if I started here and went to here, all I've done is I've gone negative 2I. And if I take a look what happened in my J direction, I went up 5 and then I went up 3 more. So I went up a total of 8. So we have plus 8J. Or if I take a look at this, if I would go up to this point right here, how many do I have to go up? Well, I would go up 5 here and I go up 3 here, so I'd go up a total of 8. So my resultant vector, is negative 2I plus 8J. Now, I did not need to do the diagram here. If I take a look at what do I have? Here's my 2 vectors, Victor. If I just add down my columns, I got 4I plus a negative 2I, I get negative, or minus 6I, I get negative 2I. I get 5I plus 3I, I get plus 8J. So I can just add the individual components, to be able to get a resultant vector. Victor. Now what I want to find is I want to find the magnitude of A plus B. By what we just did up above, we can just look at the components of this right triangle. I go negative 2 here, I go 8 up, which is negative 2 and 8. So we have VR squared is equal to negative 2 squared plus 8 squared. So we have 4 plus 64, which is 68. If I take the square root, I have the square root of 68, which can be reduced down to, let's see, 2 square root of, this is square root of 4, square root of 17, I think. 28, yeah. So we have 2 square root of 17. Now what happens when we put scalars to the 2a and the 3b? Nothing much. We just deal with the distributive property. So if A is equal to 4A plus 5J, 2A is going to equal 2 times each one of these components. So we have 8I plus 10J. (3b), or I get a negative here, so I'm going to boom chain that up to the negative. Negative 3b is going to equal, I'm going to multiply everything through by 3. We have 18I minus plus a negative 9j. I just multiplied each one of these values by a value of negative 3. And now I can add these down to give me 26I. 8 plus 18 is 26 plus 1j. 10 plus a negative 9 gives me 1j. To find the magnitude, once again, I can just square each of the components. So we have VR squared is equal to 26 squared plus 1 squared. So we have 26 squared, I'm sorry, I don't know that one, is 676 plus 1. So we have 6/7 square root of 677. And if I want to take in a decimal approximation, I can do that. Second square root, second answer, 26.02 units. Let's take a look at a couple problems down here. I want to write the component or write the vector in component notation. The magnitude of V is 10, the angle is 240 degrees. So if I draw a picture of what I have here. 240 degrees is going to take me down into this quadrant. This is 240 degrees. This is where I start. This is my terminal point. My initial position, my terminal position. I go 240 degrees. I want to write as components, which means I want to write as IJ notation components. So if I was going this direction, and this length of this is a value of 10, and 240 degrees. What would be my horizontal and vertical distance I would have to travel here? So I want to go 10 at 240 degrees, but I want the horizontal and vertical components. So if I take a look at what we have here, 240 degrees, we have 60 degrees there. Okay, I can use my Pythagorean triple idea, or my Pythagorean's ideas, or 1, 2 square root of 3 if I wanted to. But really, to be able to find our components, if you remember back to what we did yesterday, the horizontal component will always deal with cosine, and the vertical component will always deal with sine. And if you're in your values of theta, which means it's an east reference, I could do a couple things here. This value here is going to be 10 sine of 60. This is going to be 10 cosine of 60 that I can clickety-clack through. 10 cosine of 60, I get 5. 10 sine of 60, I get 8.66. But I have to remember, if I go to the left or go downwards, I need to throw in negative signs here. So I can rewrite this vector as 5i, negative 5i, minus 8.66j. The horizontal component will always deal with cosine. The vertical component, we will always deal with sine. But what would be nice about this, once we start working with these, and you work through enough of these, your calculator is set up for an east reference rotation. So if I would take 10 cosine of 240 and 10 sine of 240, 10 cosine 240, what happens is the negative comes out for us. The 10 sine 240, I get negative 8.66. They come out for us. So your horizontal component is your magnitude of the vector cosine of theta I, magnitude of the vector sine of theta j. And this works for any components or any vector. Your cosine will always go with your horizontal component. Your sine will always go with your vertical component. And if you're in the east reference here, you'll always come down, the negatives will come out for you. So let's take a look at one last one here. 5 pi over 3. First I would convert that into degree mode. Pi over 3 is 60. So we have 5 times 60, so we have 300 degrees. So if I draw a picture of what we have here, 300 degrees takes me to here. We have a unit of 6. We want to break this down into components. So I want to know horizontally and vertically, what do I have to do to get to this point? And once again, I could sit here and do a reference angle and throw in my 60 degree and do it that way if I wanted to. I just need to make sure I get negative there. Or what I can do is my horizontal component, I'm going to have 6 cosine of 60, 6 cosine of 300I plus 6 sine of 300J. So I can clickety-clack through my calculator. 6 cosine, make sure you're in degree mode, 6 cosine of 300. We get a value of 3. I, 6 sine of 300. I get negative 5.1 or 20 J. And this will allow me to put it into component notation. You should now be able to complete the rest of the worksheet that involves the vectors that I gave you yesterday, also the solutions with that. Tomorrow will be a review day over all this material that we've done here. Thursday will be once again our evaluations. Friday will be your makeup day in regards to if you need to make anything else up, go ahead and do that at that point. Pretty much a routine that we're getting into with the material that we're covering here. We have a couple weeks left here. We can do this. You've been doing a very good job. Continue with the work that you've been doing. It's once again allowed us to be able to open up our educational pathway a little bit more and how we learn. Don't have to be sitting in the desk here, how we would, even though we would like to, so we can sit there and chit chat and socialize with each other. I get that, but I would probably tend to guess. You guys are still doing quite a bit of your socialization going on. I don't think that you're sitting there by yourselves in the house and not having any type of social contact. That's just a guess of mine. But still, remember, keep your social distancing so we are not spreading anything and putting anybody else in danger. But please continue to get the work done. Please continue to push yourself through the material here. Once again, I have nothing else for you today. Tomorrow will be a review sheet. Thursday will be the evaluation we have. I miss you guys. I wish we were here in class still, but you know, it's our reality, so that's fine. We will make do with what we have. Other than this, I have nothing else for you. Adios. You folks have a great day.